Morning. So we are back from the break. I hope you guys had a good break and had a lot of online deals or Black Friday kind of shopping. We are going to have our last quiz, which is quiz number 7 today. And our final exam is scheduled to be for next week on Wednesday. And if I remember correctly, it's at 10:30 a.m. So in this very same classroom. Just a show of hands, how many of you think, just raise your hand if you think you're going to take the final. Okay, so at least we have more than 0. So good. So I'm going to design the problem. So I think I've been clear about how I'm going to calculate your grades. I treat the final exam as 3 quizzes. So the final exam is 3 problems. Each problem has 10 points, a total of 30 points. Whatever grade that you get out of that 30, for instance, you get 27 out of 30, I will divide that into 3 segments of 9 out of 10, 9 out of 10, 9 out of 10. And then I have this pool of 3 kind of quizzes coming from the final and 7 quizzes that you have taken during the semester. So I have 10 scores, and I drop the lowest 3 of them, and I only calculate your grade based on the top 7. And in addition to that, I have 5 points out of 100 basically because of coming from your class attendance. I don't have the class attendance numbers yet, but hopefully by Thursday I will have everything. So by Thursday, when we are done with this quiz today, by Thursday I have your grades, and hopefully by Thursday afternoon I have your class attendance scores, so you can actually look at your score and see, do you really want to take the final or not? If you're not obviously happy with your grade, you can take the final. And again, I've been having these questions about, I only missed one of the quizzes and I want to take 1/3 of the final exam. Unfortunately, that's not an option. You either have to approach all 3 problems. If you just take 1, your score will be 10 out of 30, and I divide that by 3, so it's going to be 3.3 out of 10. 3 of them, basically. Something like that. So it's not going to help you. A few other announcements. One of them is the course evaluation. I guess you guys have already received an email about evaluating the course as well as the instructors. I got an email yesterday that only 33% of the students have completed the survey. Please go ahead and do so. This is kind of my feedback from you guys. I have been providing feedback to you guys through these quizzes and the grades. You know, so you can see how you're performing in the class. But this is my opportunity to have some feedback from you. And if you are answering the questions, please read the question carefully. Some of the questions are related to me as the instructor of the course. Some of the questions are actually relevant to the course itself. So, you know, just make a distinction between them. So that was one thing. The other one was the Granger Award. I talked about this earlier in this class. This is only applicable to U.S. citizens. So if you are graduating this semester or even next semester, you're eligible to apply. If you want to know what is the form and stuff like that, just go to power.msd.edu. That's the website of the Power Group. And then go under awards and scholarships. And the top one is the Granger Award. The amount is $5,000. And for instance, so the basic requirement is having 3 courses in the area of power if you are an undergraduate student. And this is the list of courses. For instance, all of you undergrads have to take 1 power elective, which is 205 or 207. And then you are in 353, so that's 2 out of 3. And the third one, you can either take it next semester, or it could be another course that you have taken in the past, or it could be your senior design project advised by one of the power faculty, which is myself, Dr. Crow, Dr. Shamsi, Dr. Kimball, the 4 of us. So this is about the Granger Award. The application deadline is, I think, and you need a recommendation letter and stuff like that. I think the deadline is like January 15th. January 15th, yeah. So before even the next semester starts, you should actually submit your recommendation. And I think you have to just email it to Dr. Crow. Usually we have about 15 to 20 applicants, and we usually award around 10. So the chances are about 50%. So that's a good chance. What else? Any questions? Yes.
Topic number 3, which is series resonant converter, we didn't cover in the class.
Series. Okay, I may have, let me see. I may have given you the wrong information. What I meant by that was this one. Series resonant inverter. I don't know. Did they say series resonant converter? This is the topology that I meant, and we covered it the week before the break.
Question number 3 in the homework sample 2 was not mentioned.
That's right. So I posted another sample homework assignment for the resonant or soft switching converters, and the reason that I did that, problem number 3 on the number 2, the new one, is some sort of a converter, and we have not covered it yet. That's true, but that is independent of the topic for the quiz. The topics for the quiz was ZCS buck, ZVS buck, and this one, the load resonant converter, which is this particular one, which is a series resonant inverter. Okay. Other questions? Okay. So we're going to have the quiz towards the end. I see some of the students are not here yet. So let's see what we have done so far as long as chapter 9 is concerned. So chapter 9 is basically resonant converters. The idea is you add some sort of a cap and some inductor in the system, and ultimately you get some resonance behavior between these components. And the objective is either to have a sinusoidal signal. For instance, you are trying to create and to make an inverter, and having a purely sinusoidal signal is very important to you. Or you can achieve, for instance, ZVS, zero voltage switching, or ZCS, zero current switching through this resonance. We have analyzed and you can categorize these converters into resonant switch converters, resonant load converters, and resonant kind of a DC link converters. The first ones that we analyze are resonant switch converters. The reason is we are adding these resonating components around the switch or the diode. Like this particular one is the Bach topology, and you can see we have added a resonating inductor in series with the switch and a resonating capacitor in parallel with the diode. Ultimately, we have already analyzed this. You can achieve some zero current switching features for the switch using this topology. And remember, these are not the main. This is the main inductor, and this is the main cap in the topology. They are not the main. They are different. And then the second topology that we analyzed was, this time we added the resonating cap in parallel with the switch and the resonating inductor in series with the switch. And we didn't really do anything for the diode. And as it turns out, this one provides some zero voltage switching for the particular switch during the operation. Unfortunately, these topologies provide ZVS or ZCS, which is good, but at the same time, the analysis is more complicated. The voltage transfer ratio is hard to obtain, and the operation of the system is dependent on a lot of parameters. For instance, the value of your load, or the switching frequency, things like that. So these are kind of the disadvantages. So these kind of converters are really suitable for some application that, for instance, your load power is very constant. If you have a wide range of, for instance, variations for your input voltage or your load power, they may not be very suitable. Then we analyze this one, which is a load resonant converter, and the reason is you can see we are adding these resonating components around our load basically. So the resonance is happening in the vicinity of the load, so it's called a load resonant converter. This particular one that we have already analyzed is basically an inverter. So basically, if I just redraw this, you can see this is kind of an H bridge that we have seen before. So we have seen H bridge based inverters before, and the only difference over here is before we had this inductor and the load, now we are adding a cap as well. And we saw this last time also. We had some simulation files And you could actually see that if you tune the system very well in terms of the quality factor of the resonance component and also the switching frequency, you can get a very nice looking sinusoidal current as well as voltage, because this is a resistor, you know, a signal over here. So you can actually provide a very good, in terms of total harmonic distortion, very low total harmonic distortion kind of a signal. And as well as some ZVS and ZCS for some of the switches. So this is what we have already analyzed. What we are going to analyze today is this one. Now, the first one that we analyzed is an inverter. The objective is to create a sinusoidal signal across the load. Over here, it is a DC to DC converter. So we have this DC source over here. And the goal is to have a DC output voltage. And in between, we have basically like a half bridge over here. So we have a half bridge over here. If you remember when we were talking about DC to DC converters, one of the converters that we analyzed was the half bridge converter. And this is actually the same thing. And on the output side, so basically we have this half bridge inverter. Then we have this resonating inductor and this resonating cap placed in series with each other. So that's why it's called a series resonant converter. And then the idea is basically you will have some resonance going on. So the idea is this inductor current is supposed to be almost sinusoidal. And then your objective is to create a DC signal on the output. So what you do is you use a full bridge or sometimes a half bridge rectifier to rectify this AC signal that you have generated. And then ultimately you have a DC signal on the output. And instead of using a full bridge, you can also use a half bridge rectifier on the output side. And this is another example for that, basically. I'm surprised. Yeah. So as you can see, instead we are using a half bridge rectifier over here. So this is the topology that we are going to analyze today. So remember the objective is, so it's called a load resonant converter because the resonating components are added around the load, or ultimately you're going to see you can actually have an equivalent load for this right hand side of the topology, and it is a DC to DC converter. Okay. Okay. So I have this circuit over here, so please pay attention. We are still covering load resonant converters, and this particular one is a series resonant DC to DC converter. All right. So as I mentioned earlier, we have this half bridge rectifier inverter over here, the full bridge rectifier over here. This is our load, and this is where the resonance is actually happening. So we are going to make a bunch of assumptions. On the half bridge side, like we have done in the past, we are assuming that these two caps, C input number 1 and C input number 2, are relatively large capacitors. That means their voltage is almost constant and DC, and they are splitting the input voltage. So if I measure the voltage drop, a voltage basically that appears across the terminals of this cap, it's half of my input voltage, and same story over here. Now this is true, and we don't really analyze it, but later you can actually do it yourself. This is true as long as this current that is coming out of this terminal, node number B, is a sinusoidal current. If it has some DC component, then you cannot argue that the voltage is Vin over 2 and Vin over 2. There's going to be a runaway happening. But that's the case in our analysis. So that's one of our assumptions. The other assumption is this output capacitor is also a large capacitor, so you can assume that the voltage drop across this cap is almost constant. So your output voltage is almost a constant DC voltage. This is the same assumption that we made, for instance, when we were analyzing the Bach topology, or all these converters that we have analyzed. All right. So in order to realize these switches, as you can see, the diodes are also mentioned over here, and we are going to see why. So technically, if you want to physically realize this switching network over here, it is basically an IGBT, for instance, and there is a diode anti-parallel with that. The reason for that is, as we are going to see later, sometimes the flow of current is in this direction positive, so you can turn the IGBT on to support that current, and sometimes it's actually negative, and what happens is the diode is going to conduct, and therefore you have like a bidirectional, in terms of current, you have a bidirectional current switch over here. Or it could be a MOSFET. And the MOSFET already has a diode inside, or if you're unhappy with the diode inside, you can add a good diode in parallel from the outside. Okay. All right. So the way we do the switching pattern is these switches S1 and S2. S1 is here, and S2 over here. And by the way, sometimes when I say the switch, I'm referring to the whole switch in parallel with the diode. Sometimes I'm just referring to the transistor in that diagram. I mean, it's a little bit confusing, but anyway, as it turns out, the way it works is for 50% of the time, we have a short circuit here. So basically, for 50% of the time on the input side, this is what we have. All right. All right, for 50% of the time, so this is point A, and I label this to be point B. Okay. For 50% of the time, A is kind of shorted to this node over here, to the positive terminal of this cap. All right. So in that case, VAB will be the voltage of the cap, which is Vin over 2, the top cap. And for another 50%, this is like 50%. And then for another 50% of the period, we open up this switch and we close this switch. Then here. All right. All right, so now if you look at VAB, it is the opposite of the bottom, the opposite of the voltage of the bottom capacitor. So VAB is negative Vn over 2. And we do this symmetrically, so one period is divided into two halves, equal halves. The first half, the switching diagram is like this. And then the second half, the switching diagram is like this. Okay. So if you look at if you basically have, for instance, an oscilloscope and measure the voltage from A to B, it looks like a square-shaped kind of a signal. Sometimes it's positive Vn over 2, sometimes it's negative Vn over 2. All right. All right. So if you look at, so this is as long as our switching pattern is concerned. Now, if you look at the operating modes, technically you can argue that we have 4 different operating modes. And you can divide it into 2 subcategories. And in some of these operating modes, this current, the current of the resonating inductor is positive, and in some of them it is negative. Okay. So in the sum that is positive, so if the resonating inductor current is positive, you can actually argue that you have 2 modes. Mode number 1, and that is switch number 1 is on. Therefore, we are basically here. Therefore, from A to B, I have Vn over 2. And this current is also, we argued that it is positive. So if this current is positive, that means the conduction path for the output diodes are like this. All right. So if the inductor current, the resonating inductor current is positive, DR1 and DR2 are the ones that are going to be conducting. And if I label this to be point C and point D, if you look at the voltage from C to D is actually the output voltage. All right. So that's why here I am drawing the output voltage. All right. So this was mode 1. Mode 2, still we are assuming that the current of the resonating inductor is positive. That means it's still DR1 and DR2 are conducting, and therefore from C to D nothing has changed. You still have V out connecting C to D. But on the output side, we are actually using this mode now. On the input side, I'm sorry, we are using this mode. So from A to B, instead of having Vin over 2, now we have negative Vin over 2. All right. So these are the first two modes that you can identify, assuming that the output current is positive. Now the other two modes are created under the assumption that the output current is negative now. All right. Now if the output current is negative, so what happens is, now that the output current is negative, that means this diode is going to conduct through the load, something like this. All right. Now you can see that DR3 on the output side, on the rectification side, diode number 3 and diode number 4 are the ones that are conducting. And again, if you measure the voltage from C to D, it is actually negative of V out. Okay? Because kind of C is connected to here and D is connected to here. So C to D is the opposite of V out basically. So when the output current is negative on the output side, or whenever we are connecting C to D, we have negative of V out over here. And that's why I'm showing here the polarity has changed. All right. But on the input side, depending on what switching mode we are we applying from A to B? Are we turning switch number 1 on, and are we applying Vin over 2? Or are we turning switch number 2 on, or basically we are applying negative Vin over 2? So that's the distinction between mode 3 and 4, depending on what we are applying. Is it negative Vin over 2 over here, or is it positive Vin over 2? Okay. So bottom line is we have two possibilities for our switches, or from A to B. Is it Vn over 2 or negative Vn over 2? And they have two other possibilities for the output depending on the polarity of the current. Is it from left to right or right to left? So total we have 2 times 2. We have 4 different modes. All right. But if you want to kind of summarize all of these modes, you can argue that a large system like this, a large converters like this, could be modeled with a converter like this, or a network like this. All right. So from A to B, sometimes we have Vn over 2, sometimes we have negative Vn over 2. So if you look at this voltage source over here, it looks like this. All right. And on the output side, from C to D, we almost have the same thing, a square shape, but it's not necessarily in phase. So I'm actually going to create some phase over here, some phase shift. And that would be either V out or negative V out. And obviously the source on the left from A to B is providing power. The source on the right from C to D is actually absorbing power. It's like your load over there. All right. So technically we have a resonating inductor placed in series with a resonating cap. On one side we have a square shape coming from our source. On the other side we have another square shape coming from our large output capacitor. All right. So So this is a very kind of a simplified version of the system. Now, depending on the resonance frequency of the network, remember we have an L and a C, therefore the resonance frequency is, all right, something like this. And also we have a resonance, we have a switching frequency, and that is, okay, so the switching frequency is how I determine my switching period on the left side, because that's the only place that I have switches. So my switching frequency, omega s, is 2 pi over the switching period, and that's it. All right. So depending on the ratio between omega s, which is representing our switching frequency, and omega naught, which is the resonance frequency, we can actually observe different behaviors in the system. Usually, omega s and omega naught are very close to each other, and otherwise you don't really get a good-looking signals. And like in the analysis that we are about to have, the assumption is, let me see where the assumption is. Okay, I don't have it. Okay, here. Is that the switching frequency is slightly larger than the resonance frequency. Okay, so just keep that in mind. It should be a little bit larger. If it is a little smaller, almost you get the same results, but if it is drastically larger or if it is drastically smaller, you're going to get totally different results. All right. So let's look at some of the waveforms. Just move this over here. Okay. So what I can do is, again, you are looking at a periodic waveform on the input side, a periodic waveform on the output side. What you can do is you can break down these periodic waveforms into their fundamental sinusoidal harmonic. So I can argue that or maybe even before doing that, let me just give you some waveforms first, and then I can do that maybe. All right. I don't know if I should redraw these. All right, maybe just redraw these figures over here. All right, so let's look at VAB. We already drew it. It's a periodic waveform, and 50% of the time you are at Vn over 2, and the other 50% you are at negative Vn over 2. Okay. Okay. Now, let's plot the output, the VCD voltage. It's a little bit phase shifted. Please pay attention to the phase shift. All right, something like this. So this level is V out, and this level is negative V out, okay? And if you plot the waveform of the resonating current, basically, this is what I'm talking about. This current over here, okay? Or basically this current over here. If omega s, the switching frequency, and omega naught, the resonant frequency, are very close to each other, this current is going to be almost, and I say almost, not exactly, almost a sinusoidal current. and it is in sync with VCD. So whenever VCD crosses 0, this current also crosses 0. All right, something like this. Something like this. I mean, if you do the simulation, it is actually kind of, you can divide it into 4 segments. Each segment is a result of a resonance, so it looks kind of sinusoidal, but it is not exactly sinusoidal. You can see a little bit, even visually, you can see a little bit of a distortion in it. And technically, you can argue that here you are in mode number 1, because ILR is positive and VAB is also positive. Then you are in mode number up to this point. Let me draw this with blue now. Then you are in mode number 2, because the inductor current is still positive, but the output, the inductor, VAB voltage is negative, and as it turns out, mode number 2 is all the way down to this point. All right. Then you go to mode number 3, and that is why, because as you can see, VAB is positive and ILR is positive, and that would be, wait a minute, VAB positive, ILR positive, that's mode number 1, I think. Yes, that's mode number 1. All right. Then from here to here, so this is mode number 1. Then from here to here, you can see VAB is positive, ILR is negative, so that's mode number 2. And I'm sorry, this was not mode number 2. This is actually mode number VAB negative, ILR positive. VAB, ILR negative, positive, VAB negative. That is mode number 2. Okay, so here ILR is negative, VAB is positive, so that's mode number 4. All right, and from here all the way down to here, you can see VAB is negative, ILR is also negative, so we are looking at mode number 3. So this is kind of the sequence of the modes that you are actually looking at. So we are using all 4 modes with different length depending on the resonance that is going on in the system. All right. If you are particularly interested in one particular element in the system, for instance, let's just focus on switch number 1, okay? And by switch number 1, I basically mean transistor number 1. So technically, I'm looking at this current over here. All right. I'm not considering the current of the diode in what I'm going to draw. I'm just going to consider the current that is flowing into my transistor, either the IGBT or the power MOSFET. So let's say we are interested in this particular switch. First of all, this switch is on from here to here. So we only have to focus on this portion. For the rest, it's 0 basically. So let me just draw it down here. Okay, so I'm looking at this current. I already know this current is 0 in the second mode, in the second half basically. So no current here. And because we are looking at the transistor, this transistor is only conducting current from top to bottom or whenever ILR is positive. So from here to here, that the ILR is positive, I can argue I have some action going on. Before that, like around here, ILR is negative, so the transistor is not really conducting. It's actually the diode anti-parallel with the transistor that is conducting. So this would be our current waveform. All right? And this again repeats itself all the way when you go back to ILR positive, positive, negative, positive. Yeah, somewhere around here. Okay, somewhere around, let me see, positive down here. All right, okay, something like that. Actually, I'm not quite sure. Maybe I should just cross this out because I don't think we have a I have to confirm this. I don't think we have a conduction for the switch over here. All right, or maybe we do. Let me see. Yeah, I don't think we have anything going on over. So this is the current of my switch number 1. What about the voltage drop across my switch number 1? Basically, we are looking at this voltage drop over here. Okay. So I know when VAB is positive, this is a shorted, so it's 0. Whenever otherwise, it's actually Vin over 2. So in the first mode, the switch is on or the diode is on. Either case, we don't have any voltage. Otherwise, it's Vin over 2. Okay, something like this. So I'm in particular focusing on this particular switch to see if do we have any ZVS or ZCS thing going on, and actually we do. If you look at the current of the switch, when you turn the switch on or when the system basically forces the current to change its polarity, the current actually is crossing from 0, and therefore we have ZCS over here. At turn on. But obviously during the turn off, we don't have ZCS because you can see the current actually jumps down. So there's no ZCS there. Also, if you look at the voltage of the switch, you can see this is the point that the commutation happens between the diode and the switch. And in either case, there is no voltage drop across the switch. So you can see even here we have ZVS for S1 at turn on. Because right before the switch turning on, we have the diode was conducting, so therefore there's no voltage drop over there. So you can see for S1, for instance, at turn on, we have both ZVS and ZCS, which is a good thing. You can argue that it actually minimizes the switching losses or the noise, the electromagnetic noise that the system is emitting. All right, any questions? Okay, so no questions. We are going to continue with a little bit of a derivation approximation for the finding the voltage transfer ratio of this converter. Okay, how are we going to do that? We are going to make a bunch of approximations. Instead of VAB being a square shape, I can argue that I can only focus on the fundamental harmonic of this guy. And instead of VCD being a square shape, you can see, okay, it has a fundamental harmonic. All right. So what is the amplitude of this fundamental harmonic? 1 means we are only focusing on the fundamental harmonic. And this turns out to be, remember, if you have a square shape, it's 4 times the amplitude over pi. Or in general, n pi, n is 1, so it's actually just pi. So this gives you, so 2Vn over pi is this amplitude. For VCD, we can do the same thing VCD, only the fundamental harmonic in terms of amplitude. Again, it's 4 times magnitude of the signal V out over pi. That's it. All right. So we have the amplitudes on the input side. We have the amplitude on the output side. So this is actually okay. The other thing that we can argue is ILR is almost sinusoidal, and what happens is we are rectifying ILR. So technically, if you look at this current over here, it's the rectified version of ILR. All right? And if your cap is very large, the output current is almost DC. So you can argue that the output current is the average value of the rectified version of ILR. So I'm saying I out is the average value of the rectified version of ILR. Okay, rectification means getting the absolute value of the signal, and then you take the average value of that. So this is rectified ILR, and this is I out, and this is ILR. So ILR first gets rectified, so you get the absolute value, and then you get the average value of that. Therefore, you get a relationship like this over here. All right. So having that said, if I assume that ILR just is one fundamental harmonic, or I'm only focusing on the fundamental harmonic of ILR, I can write this equation. I out is 2 over pi times so if I only focus on the fundamental harmonic of ILR, or I just assume that ILR is a purely sinusoidal signal that only has one fundamental harmonic, the absolute value of that, and if you get the average value of that, you get an expression like this basically. 2 over pi times this. All right. So I have these three equations. So what I can do is I can use two of them to define an equivalent resistance. Okay. R equivalent resistance, this is how it is defined. Look at VCD, just the fundamental harmonic, and look at ILR, just the fundamental harmonic. All right? So I already wrote this. VCD in terms of fundamental harmonic amplitude is 4V out over pi. ILR using this equation is pi over 2I out. So I'm looking at all right. So this equivalent resistance is kind of representing our load. However, this load is being transferred to the other side of the rectifier, so it's just 8 over pi squared R. So technically what I did was look at the fundamental harmonic from C to D, look at the fundamental current that is going there, and then divide them by each other. Therefore, you can argue that this is our R equivalent. All right? And it's proportional, obviously, it's representing how much power is consumed in the system, so it's proportional with our load. So technically, I can reduce this circuit into this. All right, and even instead of this source, I can consider I have a sinusoidal source, and that is basically VAB fundamental harmonic. Okay, so you'll keep reducing the system so that in the end you have something that you have seen in circuits one AC source and a linear network of resistors, capacitors, and basically a bunch of impedance. So it's now easy for me to, for instance, find this current. It's now easy for me to find this voltage, and just keep doing that. All right. So now that we have this equivalent resistance, you can argue that or let me redraw this over here, down here. All right, so we have something like this. So now that we have such a simple AC signal, I can argue that I have more like a impedance division over here. First of all, I know by approximation, this is 4V out over pi, and this is 2V in over pi. All right. But by looking at my network now, I can argue that I have a resistive division or an impedance division. So it's RE divided by the magnitude of this impedance. All right. So what I did is just say, okay, look at this impedance, which is just a resistor, then divided by the entire impedance in the loop, which is the resistor plus the impedance of the inductor plus the impedance of the capacitor, and then that's it. That's your basically impedance division. Now, so you can see on one side of the equation I have the DC value of the output voltage. On one side I have the DC value of the input voltage, and then the rest are the parameters in the system. So if I just simplify this or rearrange this, I will get to this. Omega LR minus 1 over omega CR over RE. All right, something like this. And omega or omega S are basically the same thing. It's a switching frequency. All right, so we kind of, by approximation, we can actually see the voltage transfer ratio between the output and input voltages. Now, if you plot this thing, this is going to look like so on the x-axis, I have my switching frequency, which is omega, normalized by the resonance frequency, which is omega naught. And the action, most action I get is when they are equal with each other. In other words, the inductor and cap are basically going to cancel out each other. So I get a voltage transfer ratio of 0.5. And the reason it's 0.5 is because we are using a half bridge kind of a thing on the input side, and we are already at the very beginning, at the earliest stage, we split our input voltage. That's why 0.5 kicks in, and the voltage transfer ratio looks like a bell kind of a curve. So you can see by changing your switching frequency, you can actually change the value of your output voltage in each direction, and amazingly it's the same. So if you increase your switching frequency just a little bit, your output voltage is going to go down. And at the same time, if you decrease your switching frequency just a little bit from the resonance frequency, again, your output voltage is going down. And then you can argue that depending on what the quality factor of my network is, I can get different, basically, curve. So this is a low Q, and this is a high Q. Now, what was Q? Q was the relationship between, Q was the quality factor, the relationship between the characteristic impedance and the load resistance. All right, so depending on, that gives you a hint about picking up the values for LR and CR with respect to the amount of load resistance that you have. The other thing that you have to point out is V out over Vn is always less than 0.5. It's like a kind of a buck kind of a mechanism going on here as well. So we cannot really boost the topology. Now, a topology like this may not be very useful. However, because there is no isolation, okay? In the end, if there is a fault in the system, that whole fault or fault current is going to be reflected on the input side. But since most of the signals over here are kind of AC signals, you can argue that you can easily incorporate an isolation transformer in here as well, so that you have an isolated kind of a converter. And it's interesting enough, these days a lot of projects or people are talking about, for instance, wireless charging for a vehicle or for your cell phone. You just put your cell phone on the desk, and without really hooking anything up, it automatically gets charged. So the topologies on those applications are similar to this. So we have some resonance going on, because in somewhere, like for instance, your cell phone has the secondary side of a transformer, then the base has the primary side of a transformer. So there is some transformer somewhere around here, for instance. And you need a resonance going on, because whenever you have a transformer, you better apply purely sinusoidal signal to that transformer. For that sake, to minimize the losses, you are using this weird-looking resonance converter. So on the cell phone side, you have this side of the network, and this is basically the battery of your cell phone. And then on the base side, you have the second half of the system, basically the first half of the system. So topologies like this are becoming very popular these days, because there's a lot of money being invested on wireless transfer of power for a vehicle, for a cell phone. We already have it for instance, for electric toothbrushes, those kind of things. But here, in an electric toothbrush example, they are exactly aligned. If you look at the base of an electric toothbrush, it looks like something like this. And if you look at the electric toothbrush, so when you put them on each other, they are exactly aligned with each other. In examples of a vehicle, we don't have a mechanism like this, so you can park your vehicle anywhere in the spot, and you still need to be able to charge your vehicle. So let's say this is the parking spot, and this is your primary side of your transformer on the ground, and then you may actually park your vehicle here. And then you can see that the receiver is actually over here. So they are not exactly aligned with each other. So the challenge is in this misalignment that people are working on. Or in the cell phone example, let's say this is the place that is going to give me power. I may make it on this corner, in the center, over here, wherever. So that's actually what they are working on. So the reason that I'm covering this topology is actually becoming very, very popular these days. You can actually have a startup company improving the efficiency of this topology by itself. All right, any questions? So this was another example of a load resonant converter. In what we covered before last time, it was an inverter. Over here, it is a DC to DC converter. However, in between, we have some AC signals as well. And what we are going to cover, or maybe not, I haven't really decided what I'm going to cover next time on Thursday. There is another category, another basically topology, which is this one over here. This one is called a parallel resonant converter. And the reason is, in the previous topology, the cap was placed over here in the series path of the conduction. But over here, you can see the cap is placed over here in the parallel path. So this is called a parallel resonant DC-DC converter. And then there is another topology, which is like a combination of these two. So basically, we have two caps. One of them is the series resonating cap, and then one of them is the parallel resonating cap. Okay? So these topologies are also gaining popularity. I don't know if I'm really going to cover each individual of them, but I'm just trying to bring this to your attention that these topologies exist. If your future employer is a company which is working on wireless transfer of power, you should really be good at these topologies. All right, we are going to go to our quiz number 7.